Okay, I'll go ahead and take a poll now. Thumbs up if you're able to get to the workshop materials. Thumbs down if there are problems. And feel free to shout out if you have a problem. Okay, I think I see thumbs up all around. Thumbs down. Oh, good. Okay. All right. Let's go ahead and just get started with the presentation then. All right. This is the QR code for the material, so all of you should already be on this. That's the intro-ml-22 link that I sent you all. But let's go ahead and get started. So today I'll be talking about getting started with machine learning. So a little bit about myself. My name is Sagar. My pronouns are he, him. I'm a computer science graduate student at UMD. It's my first year doing the master's program here, and I'm pretty excited to be in it. I've been working with machine learning for the past 5 years approximately, and I'm also a researcher in machine learning and computer vision. And it's my 3rd year holding this workshop. So, it's been a lot of fun for me in the past, and I'm happy to be back here. If you have any questions about any of this as well, like graduate school or doing machine learning research, feel free to ask me after the workshop. I'll be happy to talk to you all about it. The QR code we've already gone over. If there's anyone in the chat, I will actually just send this link. Oh, I see that Pramathi has already done that. So we can just go ahead and continue. Okay, so this is what today's workshop will look like. The first half will focus on just the foundations. So we'll talk about what machine learning is, the definitions and different types of ML. How does it actually work? How do we actually get into those technical details of what ML is doing? And finally, what tools can we use to actually go from those ideas into actual ML models that you can use, train, and use in your hackathon projects? Next, we'll switch over to a demo. We'll start talking about using Google Colab to get started with Python notebooks and free Python notebooks online, and writing your first ML program. And I'll end with some closing remarks on what's next, what's after this workshop. So let's go ahead and get started. What is machine learning? So there are a couple of definitions of machine learning. It's actually not very concretely defined. So the first one that you see here is by MIT Technology Review. And they say using statistics to find patterns in massive amounts of data. So this is also a purposefully vague definition. What does it mean to find patterns? What does it mean to find, what does massive amounts of data actually mean? The next definition by Wikipedia is machine learning is a study of computer algorithms that improve automatically through experience. And again, you should have a lot of questions looking at this definition. What does it mean to improve automatically? What does experience mean for computer programs? So these definitions leave a lot up to question. My own definition is that it's a study of teaching computers how to learn to make decisions. So you can tell a computer to make a decision. You can give it an if statement like you might have done in some of your programming classes and say that if you have some input, you should do something. If you have a different input, you should do a different thing. But really what we want to do is teach a program how to learn to make those decisions. So actually write those if statements and those branches and those trees to actually get to that answer. So that's why I like to say that it's the study of teaching computers to learn to make decisions. So a quick example of how this works. Maybe you have a data set of cats and dogs, and these are labeled data sets. So you know that this data set of cats are cats, this data set of dogs are dogs. You would feed it through some network. We'll just call it this black box. We don't really need to go into what it's doing right now. And ideally, if you give it a cat, it should output that the images of a cat. So that's kind of what we're trying to accomplish with machine learning here. We're just trying to make a decision on whether this image is a cat or a dog. And ideally, our network should be able to get to that output. So any questions on this? Like so far, just what I've said? Yes. I would say that AI is a larger field that contains machine learning. So AI can include a lot of algorithms that don't necessarily need to learn. You can just give them a specific data sets and they should be able to make conclusions based on that. But they're not necessarily learning how to make decisions. They're mainly applying good heuristics to kind of get to those answers. Any other questions from the room or from Zoom as well? You can just put in the chat if you have any questions, and I will leave it be. Okay. Cool. So there are a couple of different types of machine learning, and I've outlined the 3 most popular ones. The first is supervised learning. This is when you learn with labeled data. The example that's on the slides right here is called YOLO v3. It's an object detection network that essentially you give it images of these street views, and you give it labels for this box has a car, this box has a person, and so on and so forth. And you're able to learn how to find people and cars in different images. The one in the middle is called unsupervised learning. And this is learning with the structure of the data. So the example here is called Google T-SNE, and those different colors you see over there on that image are actually digits. So it's actually a visualization of different digits. And without actually knowing the labels of those digits, this algorithm was able to tell you that these digits cluster together, so they must be the same digit. So all those purples might be 9s, all those blues might be 1s. And just by looking at the structure of the data, we can say that maybe these are the same number. So that is what learning does. Finally, we have reinforcement learning, which is learning with rewards and punishment. So if your model is doing good, you'll give it a cookie and say, good job for getting me this answer. And if it's doing bad, maybe you'll give it a punishment. You won't let it have a cookie for another month. And the model can learn to optimize to get more and more of those rewards. And the example here is from the AWS Deep Racer challenge. And on the track, there's a car, and it gets rewarded if it goes along the track, finishes the track really quickly, and stays in the center, and it gets punished for going outside of the track or taking too long to complete that circuit. Kind of diving deeper into supervised learning, there's also two different types here. There's classification and there's regression. Classification is making a decision about which class data belongs to. So in that cat and dog example, that would be classification, since we're trying to tell, is it a dog, is it a cat? Regression involves more continuous values. So if you're trying to predict how the stock markets will do tomorrow, or maybe what grade you'll get on an assignment, you can use regression. So I'm explaining these types of techniques because usually, as with a lot of programming, you'll kind of just want to know what to Google to get to the right template and the right technologies. So just knowing, am I looking at a supervised, unsupervised, reinforcement learning problem? And then if you're doing supervised, if I'm looking at classification or regression, can kind of help you just find those guides, find those resources on some more things that are similar to your problem. Okay, so now let's talk about how does all of this actually work? And actually, before I move on, I'll again stop for questions. Are there any questions on anything I talked about so far? Either feel free to put in the Zoom chat or shout it out, raise your hand. Otherwise, I will continue. Okay, let's go ahead and continue. So how does this actually work? Let's take a deeper look into that model. So a model might look like this. You might have some input, and I realize that this mic goes off when I turn, so I feel a little bad doing that. So I'm just going to look forward. Okay, so you might have some input, and you might have some hidden layers in between and some output. I'll explain what this means contextually when I have maybe the next slide. So yeah. Your model consists of these layers. These layers are kind of like what your model is actually made up of, and what you're actually training once you start learning through this model. So let me skip ahead a little bit more. In each of these layers, you have functions, and these functions basically take in the inputs from the previous layer and give that output to the next layer. So essentially what you're doing is at each layer, you're doing some computation of the input, giving that to the next layer, and then so on and so forth, and you just keep going. And between these layers, you have weights. These weights change throughout your training. They kind of give the importance of what that previous input is giving to the next one. And let's imagine we're doing that cat and dog example, and we have an image of a cat. And the source is some random GitHub. I don't actually know where I got this from anymore, but it's linked on the slides. And say you're trying to get to a dog or a cat classifier like we talked about before. So then your input would be these images, the RGB values of those images. And you would kind of just feed it through this network. And eventually you'd hope that you get some probability of being a dog, some probability of being a cat. And initially your model will do really bad. Like it hasn't learned anything. It doesn't actually know what it's doing. It'll just guess, and 50% of the time it'll say it's a dog, 50% of the time it'll say it's a cat. You'll give it this cat and you don't really know what you expect. As you train this model though, you'll be changing these weights. So it'll give more importance to certain inputs, and that probability will shift. It'll try to learn to kind of get those probabilities closer to it actually being classified as a cat. So maybe initially you'll see a jump, and now your cats, 75% of your cats are classified correctly. The weights will change again. You'll go through another iteration, and maybe it'll be 82%. Yes. So it's learning based off of these like RGB values. So yeah, it's basically taking the colors of each pixel, and that's the input to the model. So that would depend. Like maybe if you gave it enough data with white cats, then it would know that if I'm looking at a white cat, it is a white cat. But it's possible that if you give it no data of a white cat, it'll never know that that's a cat. That's true, yeah. So you can take other algorithms and pre-process your data. So let's imagine that instead of looking for a cat, I was actually just looking for the whiskers of the cat. Then if I had something that could tell me here are whiskers, then I could just use that. But a good question might be like, that's not necessarily how humans might learn. When we look at a cat, we just look at a cat and say it's a cat. So the idea might be, let's try to only give it the images of a cat without any other pre-processing. Let's see if that alone is enough for this network to learn, because that would be a very powerful idea. But does that answer your question? Okay. Yeah. Yeah. So like if you had data that wasn't in images, you could use all sorts of things. So you could use audio, you could use tabular data. In this case, I'm just showing images. Images are sometimes easier to visualize than others. Okay, so let me keep going. So as you train, you'll see like this model starts to improve. Maybe your cat accuracy goes up, and eventually you see a curve off. So you'll start off with really big gains by learning from your data, but eventually you'll kind of hit the limit of your model. And let's just say by the end of this, we have like an 85% accuracy that it's a dog, 25%, or 85% it's a cat, 25% it's a dog. This is something that we're pretty like confident with, since as long as we can say that's above 50%, we're doing good. We're able to show that it's able to get the cat correctly. But all that's really happening here is that we have these layers, we have this architecture, and the weights are changing, giving more importance to some outputs and less importance to others. And we're able to eventually change these weights in a way that we can improve our accuracy. So a lot of these algorithms, like when you actually implement this, you won't have to go this deep, but it's sometimes good to know what's happening in the background, how like you're actually able to learn. And this is just a preview into what the background looks like. Okay, any other questions about this? Okay. This kind of architecture where you have a layer that connects to another layer, and every output of that layer is the input to every layer, is the input to every node in the next layer, is called a fully connected layer. So your first layer and second layer are fully connected to each other. You'll see these kinds of terminology come up when you're looking at guides and also later on in this talk. So it's good to know what they're actually called. These can also be called dense in certain languages. There are also many other layers. When you're talking about images, which we'll talk about further in this talk, you'll also look at layers like convolution layers. These layers look at patches of the image, which can be quite useful. If you think about an image, you don't necessarily need the whole image. You can also make inferences based on a specific patch of the image, like a specific, if I cropped out the image and only took maybe that ear of the cat, I could use that information and so on and so forth to find the relevant features. So convolution layers are used very commonly when you have image data. You'll see pooling layers as well. These kind of pick out the most important signals. That probably doesn't make too much sense. So for now, we can just say that when you have layers for images, use convolution, then maybe use pooling afterwards. And lastly, when you're trying to get those fully connected layers that have the input to one layer being, the output to one layer being the input to another, you'll need to flatten them into one dimension. So you'll see flattened and fully connected layers as well. And the last layer that's seen on this diagram is called softmax. That will basically output a probability between 0 and 1. So you'll see that quite often as well in classification. So the problem that we were talking about before with the cats and dogs and the percentages, you might have something like a softmax at the very end. That kind of just shows you the probability of it being a cat or a dog. And Don't worry if this diagram is like kind of complex and there's a lot happening here. That's completely okay. I just kind of want to make you familiar to the terminology before we dive deeper. And you can always revisit all of these things and look into what exactly they're doing after this talk as well, or ask me about it. And let me just check the chat. Is the total output percentage supposed to be 100% or 110? So the interesting thing, okay, let me, so here the output can just be between 0 and 1. So you might notice that these don't add up to 100%. So I could be equally confident that it's a cat or a dog in this example. That was a question over Zoom. Sorry, I should have said it out loud. They asked, is the total output percentage supposed to be 100% or 110%? And it can depend on how you implement your model. In this case, the way that I'm showing it, it just has to be that each one is between 0 and 100%. Okay. Okay, so I know that was maybe a lot. Any questions about any of that? Yes. So what pooling does is I take like a patch of my input and I choose the maximum value or the minimum value or I average them. So it's a good way to maybe reduce how much data you're looking at, especially if you think about averaging, since averaging would just mean that I'm shrinking the amount of data that I'm looking at. And this can be quite useful since you want to eventually keep shrinking until you get to that output of just one node or one value of between 0 and 1. So pooling is commonly used to do that, and it can take away a lot of noise from the input. So again, I might be going a little bit too far by talking about noise and things like that, but I hope that kind of answers your question. Any other questions? Okay, so let's keep going. What tools can we use? So there are a couple of different tools that you can use to process all of this data. NumPy can be used to work with these multi-dimensional arrays. So when I talked about images, you can think about it as an array of height times width times the number of channels. So that can be a huge array that you need to work with. If you're working with audio data, you might have similar arrays of data, the frequency of the sound and so on. And if you have tabular data, you can have that as well. So NumPy is a pretty useful library that you'll most likely end up using to just load and work with your data. SciPy is used for scientific and technical computing. It has a lot of built-in algorithms that you can use, especially for unsupervised learning. So it's a pretty useful library there. And you can check out their guide pages and take a look at all the different algorithms that they include. OpenCV can be used for real-time computer vision. So it's a very fast library that can give you a lot of results on images and videos as input. It can also do things like simple things from grayscaling to more complex things like finding edges in pictures and so on and so forth. And you can use those as inputs to your model, or you could even just stop right there and just use only OpenCV. It also has some classifiers built in as well, so it's a good library to use. Pandas is used for data manipulation and analysis when you have those CSV type data, so comma separated data or tab separated data. You can load in those as data frames and operate on that data. TensorFlow is used for working with machine learning models. It's just one of the frameworks. There's others like PyTorch that can be used to do this. So this is where you'll be able to actually create your models, train them, and test them out and evaluate them. So in this talk, we'll use TensorFlow, but there are also other frameworks out there that you can use. TensorFlow is just one of the more popular ones. Finally, there's Matplotlib that can be used to display data, display graphs and charts on how your model is doing, or display images as well. So that's a pretty good visualization tool that you can use when you've trained a model or you're just looking to explore your data. So here are just a couple tools and technologies. There's a lot more than what I have here, but just a few to get you started. Okay, so then kind of moving on to how to actually build a machine learning model for a hackathon. So when you're thinking about building a machine learning model, you're going to first want to start at obtaining a data set and cleaning your data so you can process it. So the very first thing that you should do is look up different data sets, download them, make sure that they're not incredibly big. If you have a 1 terabyte data set, you're not going to be able to do anything with that in a hackathon. So make sure you choose smaller data sets that can show that your idea is good and that your idea is powerful. The next thing, once you have that data, is to choose a model and an architecture. These can kind of be found by just looking online. If you know that your problem is a supervised learning problem that involves classification, you can just look for what people have done in the past. It can be quite difficult to just like make these up on your own. So it's definitely better to start with a guide, start with a reference that can give you an idea of what this model should look like. Once you've chosen your data, you have a model, you'll then need to start training your data. And this can just involve a few lines of code to take that model that you just got on the previous step and the data that you got the 2 steps before and just train that model on it. But it will require time. So the thing that you want to watch out for when training a model is that it might take a couple minutes, but it could also take up to an hour, and depending on the type of model that you're doing. So when planning out for a hackathon, definitely try to train that model earlier. Once you have a trained model, you'll want to evaluate that model and see how well it performs. So this evaluation will just tell you, maybe I'm 80% good at my task of classifying dogs and cats. And that's what I want to present at the demo. That's what I want to say. My model can do this well, and I'm able to show these results. Or if you're just using machine learning as part of a bigger project, and sometimes it doesn't work, you can just explain that by saying, oh, this is only accurate 75% of the time. So 1/4 of the times it won't work now, but maybe we could do more work later to improve that. The last step is also to deploy this model and allow users to actually interact with it. So we won't talk about this step in this workshop, but the next workshop, which is at 8 p.m., we'll kind of dive into, once you have this machine learning model, how can I deploy it? And we'll do this using a website. So we'll have a web page that's running a machine learning model, and I'll talk about that in a couple of hours. But for now, we're just focusing on these 4 steps. Okay, any questions about this? Just the overall workflow for working with machine learning during a hackathon and what things you should watch out for. And I'll also check the Zoom chat just in case. Yes. That's a good question. So the question was, where can you look for obtaining data? There are a couple of websites that you can just find data on. I think the most popular one is called Kaggle. Kaggle will have a lot of data sets that are available for open use, and you should find all sorts of data. So data, images with audio, so on and so forth. You should also just be able to Google a data set. If you read about a data set, a lot of them also come with the research papers. So those research papers will also introduce a new data set and publish them on their university web pages. So that's another place to look. That can be a little bit harder to find though, since there's not just one place you can search for them. But if Kaggle doesn't work and you think it's in some research, you could try searching Google Scholar and look for this data set and see where if they published it or not. That's like the 2 sources I would recommend. Any other questions? Okay, let me move on. Okay, so now let's kind of jump into the more demo side of this workshop and talk about using Google Colab. So Google Colab is a free tool that you can use to build interactive Python notebooks and work with machine learning. It's pretty nice. You can even get GPU instances, which are usually very expensive, for free. And you don't even need a Google account, but if you do sign in, you can save those notebooks and store them. So I'm gonna actually go over and switch to the folder that I have. So if you're on this folder and you have, so if you're on this folder, it was the one that I linked at the very beginning. It was the go.umd.edu/intro-ml-22. You should be able to see all of these files. Let's start with the first Colab notebook file here. So in this drive folder, I've included both the template, which we can, if you want to follow along with me and work on it, then you can use this template. If you don't want to follow along, but you just want to see the solution, I also have that. So we'll have, for every file, we'll have a file and also a template file. I'm going to go ahead and open the template file so that you all can follow along with me. But if you open this file, you should see this page open up to Google Colab. The first thing they're going to do before we even jump into this file is create a copy of this file. So I'm going to go ahead and click Save a Copy in Drive so that I have a copy of this. Otherwise, you won't be able to edit this file. And if you do edit the file, you won't be able to save it. So just go ahead and create a copy. Is everyone able to go to this notebook and create a copy of this notebook? And are there any technical difficulties that I can help out? Yes. I imagine the Wi-Fi will cause issues throughout this workshop, yeah. I can ask for a survey, and I can also wait like a minute so that if there is a chance of everything loading, that you'll have a couple of moments before I keep going. I'll resume at like 4:01. If you have any questions in between, then we can talk about that as well. How do we copy it? Yes. So if you're trying to copy this notebook, and let me zoom in, because I realize this is kind of small. Okay. If you're trying to copy this notebook, there should be a file button here on the left corner. Then you should be able to click Save a Copy in Drive. And this will allow you to create a copy of the notebook. And we're working off the template, but if you just want to see the solution, you can just click the solution and read along. Okay. And okay. How is everyone doing? Are we here? Okay. I see some nods around the room. Everyone else is head down on their laptop, so maybe I'll take that as a good sign. Okay. So let me go ahead and get started with going through this notebook. So the first thing that you'll see is that this notebook has these buttons for code and text. So in these notebooks, you can create code cells and text cells. Text cells can help you describe the code that you have, great for showing a demo. And code cells can help you actually write the code that you want to write and run it. This is pretty similar to Jupyter, if any of you have used Jupyter before, but if you haven't, completely fine. That's what we're all here for. The first thing that you're going to want to do is click Connect. So there should be a Connect button on the corner, and this will connect to a runtime. If you hover over this, you should see that it says connected to Python 3 Google Compute Engine backend. And that way you are connected, you can run code here and continue with this workshop. Okay. So the next thing that you're gonna see on this page is that you also have this folder tab here. If you click it, you'll see that this is where all your files are stored. Right now, it should just have some sample data files and nothing more. And you can use this to basically upload files to use for your any training that you're doing, any data that you have. You can also link this to Google Drive, and that will kind of just give you give Colab access to your entire Google Drive and all the files that exist there. So you can do that as well. And that can be a little bit easier sometimes, since you don't have to re-upload files. Okay, so that's files, and that's on the runtime. So now let's just do a few simple code blocks. So I have this hello world code block. If you haven't typed Python before, Python is relatively straightforward. It's a lot like English. You can just do print and then in quotation marks, hello world. And this should just print out hello world. Now, if I wanted to go and print out a range of numbers, that can just be done with a for loop. So I could do for I in range 10, print I. And what we'll kind of see here is that you have your code and the output right next to each other. You're able to see like the output directly below it. Pretty useful as well, since you don't have to like write an entire file and run it. You can run it simultaneous to you writing it and just test out that your code is working correctly. Okay. The next thing that you might want to do is display an image. So to do this, the first thing I'll need to do is upload an image. So I have one in my downloads, and you probably have an image somewhere as well. I realize I have many. Let me just choose a random one. I'll choose this QR code. I don't know which workshop it's for, but we shall find out. So to load an image, we can just we've used this matplotlib library that I talked about previously. To read an image, it's just image equals plot.imread. So image read is what that stands for. And give it the file. So frame-4.png. Okay. Next thing I will want to do is show that image on a plot. So then I'll do plot.imShow image. Finally, I want to show that plot. So plot.show. Okay, so in these 3 steps, I've kind of created this plot. I've loaded in this image and shown it on this graph, and you're able to see the scan me code. You can try this out with an image that you have. So just feel free to upload any image to Colab, and then just make sure that you change this file name to whatever that image's file name is. You can do other cool stuff as well. Like what if you wanted to flip this image, then maybe I'll just say image, or I'll just say flip equals image ::(-1). I think that should flip either the height or the width. And I'll again just show this image and show this plot. So now we can see that I've kind of flipped it vertically. So just a fun example, I've basically just used some fancy Python syntax, and I'm able to manipulate these images. I've loaded them in and do different things with them, and also show them on a plot. Does this make sense to everyone? Let me actually look at the chat as well. Yes, I can go back to this step. I can also maybe zoom out a little bit so that it's more clear on my screen. Let's see, maybe not. Okay, but I think this is the step that was requested. Okay, any questions up? Maybe ever in your following along. And if you're not, you can always just look at the solution. Is just template. So you should see that there is this getting started with ML template. Go ahead. I can actually, I'll pause here for a bit. So files, this files tab over here on the left, you should just be able to drag and drop an image onto there. You can also click this upload. Okay. All right, I will move on. I will move on to the next part. Okay. I will move on to the next part if Wi-Fi allows me to. So let me try reconnecting to the Wi-Fi. Oh, never mind. Okay. So magically has come back. Started with ML template notebook, which may periodically go on and off. But okay, never mind. Back to waiting. Yeah. In the meantime, do any of you have any interesting ideas of what to do with machine learning for this hackathon? Unless maybe that's too early to say if they're like secret. But we can just talk about ideas as well. Or at least, I guess, anybody only talked about a couple types of machine learning. Is there like a problem that people think you'd like to apply to and are curious about? Yeah. So displaying a model can be like the model itself. It can be quite difficult since they get to be so big. So the model that we'll create in this workshop will have 4 million parameters. So if you think about that, that's impossible to display nicely on any like one website page. That being said, there are like good tools to do that. You can look at a summary of a model, and that'll tell you what the different layers of model look like. And that'll give you like a very good idea of what the model is doing. Another way that you can do it is you can feed it into some tools that take those weights and actually visualize them. So there's actually a really good example that I think TensorFlow has. They have this example where you can train a model on their web page, and they'll kind of show you the different things that happen. But they also have a really good visualization of like what the nodes look like and what the input looks like. So there are lots of tools. That's actually an open research area field as well. Like how I can actually visualize these models that are really big. But the easiest thing to start off with is look at the summary of the model. Yes. UI UX design. So definitely like take advantage of, if you're just asking like, how can I make this into a more formal looking notebook? Take advantage of the fact that you have those markdown cells. Those markdown cells are very useful. You can add headers, you can add text, you can add code blocks, you can add images, videos, things like that. So take advantage of those to really tie together your code and tell the story of what your model is doing. Yes. Yes. So at the end of this workshop, we'll actually like download our model. And what we're going to do is we're going to use Colab and its GPU resources to train the model, because that's very expensive. And then deploy this to a web app by using that downloaded file. That way, when we're actually training the model, which is very expensive, it takes a lot of time, we'll do that using all the free resources we get. Then when you have the actual app, that's when you can just run the model. And that's usually a lot cheaper. We'll talk about it in terms of web development, but if you're interested in like Android development or iOS development, there's also just similar ways that you could do this process. So we're using TensorFlow right now. There's something called TensorFlow Lite, which is a lighter version of TensorFlow that can run on websites, mobile phones, things like that. Okay. And I will check the chat. Okay. Thank you, Pramati. Okay, so again, let's go ahead and create a copy of this notebook first. So if you're on the Getting Started with ML Template notebook, click that File tab, click Save a Copy in Drive, and it should create a copy and open it in a new tab. Okay, now let's go ahead and click this Connect button. And in theory, it should already be connected to a GPU. But just to show you how you can do that process on your own is, if you click this runtime button at the top, you hit change runtime type. You should be able to change between a GPU, a TPU, or nothing at all. So when you're training, especially with images, you'll really want to use a GPU. That will help increase your training speeds by like as much as like 10 times to maybe 60 times as faster training speed. So definitely switch to a GPU. Coding. I would not recommend this for anyone who's just getting started, but if you do have experience and you want to use it, then Colab also supports TPU runtimes. But it should already be selected since this notebook was originally run in a GPU runtime. So if you copy it, it should also be in a GPU runtime. So the first thing that we're going to do is download some data. And I realize I'm getting ahead of myself and I didn't even introduce what we're doing. So what we're going to be doing today is making a binary classifier. This is when we output 1 or 0 for a given problem. And we're going to be doing a dog-cat classifier. So I should have hinted this a couple of times during this workshop. But the goal is that we're going to make this model that's able to look at this data set of dogs and cats and classify whether it is a cat or not a cat. So that is our binary 1 or 0. Okay. So now let's go back into the actual code and the data that we're looking at. So there are a couple different ways that we can download the data. I've done this because the first year I did this workshop, all the participants basically brought down my website. So if the first way doesn't work, go to the second way. If the second way doesn't work, try the third way. But you should see this command that says gdown and has this ID. If you run it, it should start downloading data. And we can see it's going relatively fast. But in your files tab, you should see that we have this training set.zip file. This is the training data. It should have around 600 megabytes of training data. And it's all images of dogs and cats. So that is just what the first line is doing. It's using this gdown command to download the data that I've hosted myself. If this doesn't work for you, you can try the second line. In theory, this should help if the first one doesn't, but I haven't had to go down to the second line yet in a workshop after the first one. So here's to hoping that everything goes correctly. The next thing that you're going to want to do is unzip this data. So this data is in a zip format. You want to unzip it. In Colab, if we add this exclamation mark, we're actually running in Bash. So we're running on like the computer that the Colab notebook is running on, and you can run these commands. So I can just run this this exclamation mark unzip training set.zip, and it should inflate these files and create a training set for us. And you can kind of see that we have these classes, class A, and then like the images. So we can see like dog 4,168. So there are lots of images here of dogs and cats. If you hit this refresh button on the files tab, you should see that you have this training set here. It has the two classes, and in those two classes, the dogs and the cats. So now we have our data, and I've kind of skipped that data cleaning step. I've basically just given you a data set where the data exists, and it's in these two classes of dogs and cats. The next code block here is just going to separate these dogs and cats into a training and test set. So it's pretty valuable to have a training and test set, since you want to train on one set of data and test your model on another. If I was giving you an exam, then I would maybe give you a practice exam that's on one thing, and then give you an exam that's on a different thing. It wouldn't make much sense for me to give you the same exam as a practice exam, because then you could just memorize all the answers and then write them down again. So same with machine learning models. You want to split your data into a training set that the model looks at to learn, and a test set that you can use to evaluate your model and make sure that it's doing well. So that's what we're doing here. So now if I reload this, I should see that I have now a test set here that has my two classes as well. So this code I've given to you, and you can kind of see how many images are in each of these. We have 10,000 images in the training set and 2,500 images in the test set. Okay, yes. Yeah, that's also a good question. So it's really arbitrary when it comes to machine learning. Like if you're doing research, then you'll want to just go based off of what people have done in the past, so you can compare and you have a benchmark. In this case, what I did was an 80-20 split, 80% of the data for training, 20% for testing. And that's a very common split ratio. You might also see 70-30 splits, 50-50 splits. So when you're initially doing this and maybe showing the results on your model and evaluating it, start with something that's a bigger split. But maybe for your final model, the one that you actually use in your website, use all of the data. Use every data that you have. You want the model to be as good as possible when you're actually deploying it. But for now, I was just saying that let me just separate 20% out so I can make sure that this model is actually good and not just memorizing this data. Okay. So now we're actually going to move on to building this model. And we'll use some of those layers that we talked about before. There's the convolution layer, there's that max pooling layer, the flatten to go from multiple dimensions to 1D, and the dense layer, which is that fully connected layer that we talked about. We also have this image data generator that we're importing that will take this image data set that I've created and make it into something that we can process through this model. So, and lastly, we also have a sequential import. So there are two types of models that you can do with TensorFlow, sequential and just a functional model. We're going to use sequential. Sequential is easier. It just means that one layer is followed by another layer is followed by another layer. You can have more complex models in TensorFlow, but we don't need that for a hackathon and definitely not for this workshop. So we're going to start off by just saying this classifier equals sequential. and put 2 parentheses. And this will start us off by just creating a sequential model. It doesn't have anything. I didn't run the first line. That's nice. Okay, so first I'll run the imports, and then I will move on to creating a sequential model. The next thing that I want to do is create that convolutional layer. So when you're dealing with image data, you'll very commonly see convolution layers first. So what we're going to do here is create a convolution layer. So just conv 2D. Then I will give it 32 filters. And I will preface this by saying I looked at a guide, and the guide used 32 filters first. So do not think that I made this up, that I somehow thought this through in all the math, and I was like, 32 is the right number. Definitely look at a guide and try to see what people are doing in the past to make your decisions. You'll also see that Colab gives you this nice, really helpful what the input should look like preview. So the next thing that we need to do is our kernel size. So when I was talking about convolution layers, I was talking about those patches. And I talked about how we're kind of operating on patches of the image. So this is just telling us what size that patch should be. So I'm just going to do a 3 by 3 pixel patch. Next, I will also give it a input shape. So the input shape is just telling like what kind of shape am I getting inputted to this layer. So my images are of the shape 64 by 64 by 3. So there's 64 pixels as the height, 64 is the width, and 3 is for the RGB channels. So that's why 64 by 64 by 3. And finally, I will give it an activation. So I'll just say activation equals ReLU. And we don't really need to worry about what ReLU is doing. Let's just give it this activation since we read about it in a guide. And I won't dive too deep into which activations to choose. I also have some comments that are laid out here that describes where we're using convolution layers. So if I'm going too fast or I skipped over the descriptions, then just read through. I hope I gave enough information there. So I'm going to go ahead and run this. And this will add this conv to. Next, I'll add the max pooling layer. So then I'll just do max pooling 2D. Maybe it's the first one. Great. And I will give it a pool size of 2,2. It's actually the default pool size, but I'll just explicitly write it out. So this would be when I talked about getting that max or min or average value from those patches. This is giving the patch size again. So 2 by 2 is that pool size. So I'll go ahead and run this. So now I've added a convolution layer followed by a max pooling layer. Then I'll add a flatten layer. So now I'll flatten out our input so it's no longer this height times width times channels. It's now just a 1D array. And finally, I'll finish this off with a dense layer. So I'll do 2 dense layers. So I'll do first a dense that has 128 nodes. So if you're visualizing this in your head, it's just like you have 128 nodes in that middle layer that we talked about in the diagram at the very beginning. And then I'll end it off with a dense layer with just 1 node. I'm going to stop here since I kind of just ran through this and also check on the time. And know I'm running close to, yeah, I see that time indication. Let me look at the chat. Oh, okay, great. Okay, so at this point, we have created our model. We've kind of added the different layers that we want. And next, we're going to compile it. I'm not going to, again, touch too deep into what this compilation is doing. Just know that once you've built your model, you've added all the layers you want. You can compile it by giving an optimizer, a loss, and any metrics you want to track. So in this case, the optimizer is Atom. It's a very popular optimizer. You can default use it for any model that you're doing. And like until you really care about trying to push your model like 1% more higher. So Atom is fine. The binary cross entropy is because we're doing binary classification. So you want to use this loss. This will basically help tell your model how bad it's doing when it makes those predictions between 0 and 1. Finally, we have this metric for accuracy. This is just so that we can kind of keep track of how our model is doing, and it'll basically just output the accuracy at each step. So that's what we have in this compilation commit. And we can do the summary. So this kind of answers your visualization question partially. And we can kind of see that we have this conv layer, max pooling layer, flatten, dense, and then a second dense. And like I said before, this has 4 million parameters. So definitely not something that you want to code yourself. Definitely not something that you ever want to think about trying to optimize, because just think about a function with 4 million different variables that you can modify. It would be quite hard to wrap your head around. But that's what this model is doing. It has 4 million different weights that is trying to change to kind of answer this question. Okay. Next, I have a few cells for loading the data. I'm just going to run through this so that I don't cut. I'm going to cut close to time anyway, so that's fine. And I want to leave some time for questions. So I'm just going to jump into like what this actually looks like. So ignoring the fact that I have these 3 dots and that the solution notebook contains the solution, just look at the solution notebook for the solution. But once you train it, you'll see that you get these epochs that are printed out. This tells you how many of the entire data set have you like trained on. So in this case, I trained on 3 iterations of the entire data set. And it took me about 290 seconds, so about 5 minutes to do this. And then after I was able to do this, I could also use this model with this block here to kind of show the prediction. So here I'll see that it's doing pretty well. Like it got this image of a dog that it never saw before from the test set, and it gave it a really low number. So if you're thinking that above 50% is a cat and below 50% is a dog, then this will just be 3.1%. So doing really good. We can see that it does good for a couple images with just this simple model that we outlined. So doing great on dogs. We'll see that it should have some failure cases. I don't know if it's outlined here, but here's a cat. It said it's 85% confidence a cat, so it's a cat. We can see that some cats it's less confident on, so this one is only 62.5% confident. And we can kind of do this for the rest of the data set as well and kind of get a good visualization of, now I've run my model on this test set, I've seen how it does with some input and kind of get a sense of how this model is doing. Okay, so for the next workshop, there's also these 2 lines at the bottom that will download your model so that you can use it in those upstream tasks like an app or a website. And this will just basically use TensorFlow.js to make it into a JavaScript model. But I still have a couple of minutes, and I just want to end off by going back to the slides and kind of wrapping up. So let me go ahead and do that. Okay, so we've kind of like run through this demo, but ideally, if you also go through it, maybe after this workshop, you should have a machine learning model that's able to do dog type classification. But there's a lot more when it comes to machine learning. So I kind of just wanted to end by touching on a few examples of ML. So the first one on the top left corner is by OpenAI. It's called DALL-E 2, and you may have heard about it. It's been pretty popular. It's on Twitter and everywhere, really. And you can kind of see that the input to this model was teddy bears working on new AI research on the moon in the 1980s. And just given that input, it was able to generate an image of what that looks like. So you can see that there's 2 bears on the moon working on computers. And you can just think about how hard that is to do, since like they didn't have that image before. They made that image up. It's completely fake and it's generated. There's this model called Palette that kind of fills in images. So here, if I take away this part of the image on the left, I can fill it in. And you can see it's a very realistic looking face, even though it's not really the face of the boy that was originally in that image. So it's been filled in by a machine learning model. The example on the top right is called AlphaGo. And like other models that have solved chess and other games, this one has beat one of the best players at Go. And it was introduced by DeepMind. The model at the bottom left is a reinforcement learning hide and seek model. So it's pretty interesting. They had hiders and seekers trained using reinforcement learning to hide from each other, seek from each other. And they invented new strategies at doing hide and seek that the researchers never thought about. So they used the building blocks in new ways and invented new strategies by just training on this environment. And the last example that I have here is something called NERF. It's called neural radiance fields. And it basically takes just a couple of images and generates this entire sequence of this video that you can see. So it's a very fluid looking motion of how that comes together, but it's actually just like a couple of 5 or 6 images that are used to build the entire thing. So that's really where I wanted to end off at. There are more workshops that I am doing today, so I'll just plug them. There is for beginners track, there's a demo day website workshop in 30 minutes. And there's also a workshop on undergraduate research. So if any of you all are interested in research as well, then feel free to go to that one. And finally, there's a part 2 to this workshop on hosting your ML model on the web. So if you're interested in what I talked about right now and want to know how to take it further, then feel free to meet me then. But other than that, thank you all for coming. Hope you all have a good hackathon.